In 1935, Einstein wrote a fascinating paper that attracted a lot of attention from physicists. He co-authored the paper with his colleague Nathan Rosen. In this paper, Einstein mentioned a bridge connecting two realities. These two realities could be two different locations in the same universe, two different locations in different universes, or two different points in time. This bridge later became known as the Einstein-Rosen Bridge, or more popularly, a wormhole.
What you seek, it's a bridge.
Like an Einstein-Rosen Bridge?
What's known as an Einstein-Rosen Bridge, otherwise known as a wormhole.
That looks like a collapsing neutron star inside of an Einstein-Rosen Bridge.
That's the wormhole.
Yes, the wormholes you often see in science fiction films, where a hole can transport you to another galaxy or dimension, are not entirely a figment of filmmakers' imaginations. They originated from a physics theory based on this very paper by Einstein.
Thought experiments Einstein taught us are a powerful tool for probing the nature of physics. And our infinitely advanced civilization, could such a civilization build a wormhole to travel from here to another galaxy?
So, is a wormhole something real? Let's discuss the concept of wormholes in science. At the end of this video, we'll even talk about how a wormhole could be created in Google's quantum computer.
And so in the quantum computer, we can directly send a qubit from one side of the wormhole and watch it come out the other.
And he said, "Are you destroying the world? What are you doing?"
Alright guys, the first thing you need to know about wormholes is that the concept emerged from Einstein's theory of general relativity. We've already discussed this theory in a previous episode, so if you haven't watched it, please do so you can follow along with this video. In the last episode, we explained that the theory of general relativity describes the curvature of space-time caused by the presence of large masses like Earth or the Sun.
And he says, in the general theory of relativity, that the sun, merely by virtue of being in space, warps the fabric of space, actually, and time.
According to Einstein, this curvature of space-time is what causes gravity. A consequence of this theory is that the larger an object's mass, the greater its space-time curvature and the stronger its gravitational pull. At the time, scientists hypothesized that there must be an object in the universe with such an immense mass that it warped space-time so drastically that objects nearby would get sucked into it. This object was later named a black hole. It's called a black hole because not even light can escape its gravitational pull, making the object appear dark, like a hole. The first black hole was successfully photographed in 2019 after astronomers around the world connected their telescopes and pointed them at a single object believed to be a black hole.
You are seeing is evidence of an event horizon. We now have visual evidence for a black hole.
The question is, what's on the other side of this black hole? No one knows, because not a single signal or piece of information can escape from it.
We can't get anything from it.
Nothing escapes that horizon, not even light.
But here's what's interesting. Black holes are discovered thanks to Einstein's formula, known as the Einstein field equations. According to Karl Schwarzschild, a mathematician who solved Einstein's formula geometrically, the equations should also allow for the existence of an inverse version of a black hole, later called a white hole. The difference is that while a black hole sucks everything in and nothing can get out, a white hole spews out everything inside it and nothing can get in. So, if a black hole and a white hole were connected, they would look like a one-way tunnel. This was the origin of the concept of a wormhole, but at the time, it wasn't taken seriously enough to be called a wormhole. Then, in 1935, Einstein's paper was published. Ironically, Einstein's intention was not to create a theory about wormholes, but to study the properties of particles. In his paper, he described this particle as a bridge connecting two realities, where an electromagnetic field could enter and exit through this bridge. Einstein's paper was then interpreted differently by other physicists, John Wheeler and Robert Fuller. They argued that the bridge Einstein was referring to had nothing to do with particles. Instead, this bridge was a space-time bridge that could connect 2 points in the same universe. John Wheeler later coined the term wormhole. He came up with the name after illustrating the concept with an apple eaten by a worm. He explained that a worm would take the shortest path through the hole rather than traveling across the surface of the apple.
And you live on the surface of the apple. The surface of the apple is your entire universe. You can go around the outside through the universe itself, or you can go through the wormhole.
However, a more popular illustration uses a folded piece of paper.
So they say you want to go from here to there.
We could fold the space, bring the target closer to us, create what's known as an Einstein-Rosen Bridge, otherwise known as a wormhole.
So that point A and point B coexist in the same space and time.
So you can take a shortcut through a higher dimension.
But you have to remember that the paper analogy is only a two-dimensional representation, while we live in a three-dimensional world. This means a wormhole in 3 dimensions wouldn't look like a hole, but a sphere.
Which turns a wormhole into 2 dimensions, a circle. What's a circle in 3 dimensions? Sphere. Exactly.
Everybody ready to say goodbye to our solar system? To our galaxy.
Unfortunately, from a scientific perspective, wormholes are almost impossible to exist. It's not that they're completely out of the question, but as John Wheeler said, even if a wormhole existed, it would be impossible to pass through. As soon as we try to enter, the wormhole's mouth would close up quickly before we could pass. The only exception, and this is the interesting part, is if humans could create their own wormhole using exotic matter. Exotic matter is matter that has negative mass or negative energy, and so far it's just a hypothesis in the realm of quantum physics.
So there's the issue of how can you hold a wormhole open? Well, various people have worked on it, and we now know that what you have to do is stick inside it something that repels gravitationally. That's pretty obvious. The walls need to repel each other gravitationally. And that means you have to have something with negative mass or negative energy.
This hypothesis about a man-made wormhole was put forth by Kip Thorne, a physics professor at Caltech and a Nobel laureate in the field of gravity. You should know that Kip Thorne was the scientific advisor for the film Interstellar. All the scientific concepts in Interstellar, including the wormhole, were created by him.
Chris and I brainstormed about the science every few weeks while he was working on the screenplay. And on several occasions he said, I need this, I want this. And I would respond, I don't think that can work.
In Interstellar, Kip Thorne depicts that a wormhole could only be created by higher dimensional beings or by humans in the future after they are able to harness exotic matter.
A wormhole is not a naturally occurring phenomenon.
Someone placed it there.
They.
And our infinitely advanced civilization, could such a civilization build a wormhole to travel from here to another galaxy? We simply do not have the understanding of the laws of physics to be able to speculate about that quantitatively yet. We have to have a much deeper understanding of quantum gravity to get the answer.
So far, wormholes only exist in the world of fiction, but that doesn't mean research on them has stopped. Recently, a group of researchers claimed to have discovered what they call a holographic wormhole in Google's quantum computer. How is this possible? Let's discuss it briefly. You need to know that when Einstein released this paper in 1935, he also published another paper in the same year. We have discussed that second paper in a previous lesson on quantum physics because it gave birth to the EPR paradox, which we know as quantum entanglement.
Quantum entanglement, Scott.
Surely you remember quantum entanglement, a phenomenon that shows particles can interact with each other even when they are very far apart. Einstein called it spooky action at a distance. So, what's the connection between wormholes and entanglement? This is where it gets interesting. When Einstein wrote both papers, he didn't realize the connection between them because they were written in two different contexts, one related to gravity and the other to quantum theory. But in 2013, Leonard Susskind, a professor at Stanford University who studies quantum gravity, a combination of quantum and gravity, realized that the two papers were connected and were in fact the same thing, something that Einstein hadn't realized 70 years earlier. He then proposed the equation ER equals EPR. ER stands for Einstein-Rosen, referring to the Wormhole paper, while EPR stands for Einstein-Podolsky-Rosen, referring to the second paper about entanglement. This means that a wormhole is equal to entanglement.
Wormholes and entanglement are the same thing. That was totally unexpected. One of them has to do with general relativity. One of them has to do with quantum mechanics. Didn't seem like they had anything to do with each other.
This concept has opened new hope for physicists. Although wormholes are still just a theory, quantum entanglement has been proven in practice and is the basis for creating quantum computers, one of which has been built by Google. You should know that a quantum computer basically works on the principles of quantum physics. While regular computers use regular transistors with bits as their units, quantum computers use atoms with qubits, or quantum bits, as their units. With qubits, quantum computers can be millions of times faster than today's computers. With the existence of quantum computers and the concept of ER equals EPR, scientists thought that, in principle, a wormhole could be created inside a quantum computer. So, in 2022, a group of scientists from Caltech conducted an experiment using Google's quantum computer to simulate a wormhole.
I don't think we really thought it was going to work, but we thought we would learn a lot by seeing how far you could get.
They didn't say, "You're crazy, let's do something else." They said, "Okay, you're crazy, let's do it."
We won't go into detail about how the experiment was done, but what's certain is that this wormhole was created by sending information from one qubit to another. So it was a form of teleportation. If this teleportation was successful and they observed a negative energy signal, that basically means the information passed through a wormhole.
At first I was like, this is probably just noise artifact, but as the data kept coming and the peak kept getting clearer, it was like, this is a wormhole. I think I just saw one.
He said it's there. I said, no kidding, he's there. It was nuts. It was nuts.
Unfortunately, this wormhole in the quantum computer exists at an extremely small scale, a scale known as the Planck scale. So it's impossible for us to see it with our eyes or to pass through it. But speculatively, according to Kip Thorne, a small wormhole like this could one day be enlarged by a more advanced civilization than ours, allowing humans to pass through it. Or maybe we'll just have to shrink ourselves, like Ant-Man.
They're down on very, very tiny scales of 10 to the minus 33 centimeters, called the Planck length. But there is a foam of tiny, tiny wormholes that's just bubbling and bubbling and bubbling quantum mechanically. And so you can imagine a very advanced civilization reaching down and grabbing one of these wormholes and enlarging it, making it big so it can travel through it.
So, that's the story of wormholes, guys. What do you think? Do you believe wormholes are real? Or is this just the thinking of delusional people? Whatever it is, the universe still holds many mysteries. When one theory is discovered, it opens even more mysteries. That's why Einstein said, the important thing is not knowledge, but imagination.